The fundamental theorem of calculus. What is the fundamental theorem of calculus, or the FTC? Well, it's a theorem that gives us a relationship between integration and differentiation. Part 1 gives us a formula for taking the derivative of functions that are defined to be integrals. Part 2, also known as the evaluation theorem, allows us to evaluate the definite integral. In this presentation, we will focus on Part 1 of the fundamental theorem of calculus. So Part 1. Part 1 tells us that if we start with the function that's defined to be an integral, here we see that big F is defined as the integral from a to x of f evaluated at t with respect to t. Well, Part 1 tells us the way in which we take the derivative of big F. And here's what it says. That the derivative of that integral function of f evaluated at t is simply f evaluated at x, the upper limit. And if our upper limit is u, where u is any function other than just plain x, say maybe an x squared or a cubed root of x, something like that, then the derivative is f evaluated at the upper limit u times the derivative of u. And this second part, the f of u times u prime, this accounts for the chain rule for derivatives. So in essence, this theorem is telling us that if we take the derivative of a function that's an integral, we get back to our original function. We'll look at some examples. In the first example, we're asked to find the derivative of the function that's defined to be the integral from 0 to x e to the negative 3t with respect to t. Remember that the theorem tells us how to take such a derivative, and the theorem says that we replace t in the integrand with the upper limit x. So in our case, we replace t with x, and instead of e to the negative 3t, our final answer is simply e to the negative 3x. Again, applying the theorem allows us to simply take the upper limit x, put it in the place of t in the integrand, and there we have our final answer for the derivative. Example 2, we want the derivative of the function that's defined to be the integral from pi over 2 to x of the cosecant cubed of t with respect to t. The theorem says to replace t in the integrand with x, and there we have the derivative. So we do that, and our derivative is the cosecant cubed of x. Example 3, we want the derivative of that integral function. We'll apply the theorem again and replace t with x and find that the derivative is 5 divided by 1 minus the square root of x. Now we'll look at some chain rule examples. This time we're asked to find the derivative of the function that's defined to be the integral from pi to x squared sine of t with respect to t. Notice this time my upper limit is x squared and not plain x. This means that we'll have to use the chain rule version of the FTC. And remember, that says that you still replace t with the upper limit, but you also have to multiply by the derivative of whatever the upper limit is. So we'll replace t with x squared and have sine of x squared, but then we also have to multiply by the derivative of x squared. The derivative of x squared is 2x, and so our final answer for the derivative turns out to be 2x times sine of x squared. We want the derivative of this integral function, and we'll notice again that our upper limit is 4x and not plain x, so the chain rule is required here. We'll replace t with 4x, but then we also have to multiply by the derivative of 4x. The derivative of 4x is 4, so our final answer turns out to be 4 times the natural log of 4x plus 1. Our last example, we want the derivative of that integral function. Again, our upper limit this time is the cube root of x. more than just the plain x, so we need to use the chain rule. Replace t in the integrand with the cube root of x, and also remember to multiply by the derivative of the cube root of x. The cube root of x derivative is 1/3 x to the negative 2/3. So our final answer is 1/3 x to the negative 2/3 times 4 minus the absolute value of the cube root of x.